Hey Rob and Johan, if you guys are online, I think we can get started. Would you mind turn on your camera? And yeah, we will kick off our panel pretty soon.
Yes, I'm here. The audio broke up a little bit earlier. That was the problem.
Hello. I'm here too.
Okay, so as we know that the open source intellectual property emerges an innovative revolution in both academia and industry. It greatly cuts down not only the IP cost, but also the cycle for the design iterations. However, it also draws the question is how can we ensure the innovation can still thrive in such market without the traditional IP protections? And also, what is going to be the impacts on regarding the entire ecosystem of the either the hardware design and the ASIC manufacturers? Therefore, we invite our panelists to have today's discussion regarding the open hardware opportunities and challenges. And my name is Chi. I'm the postdoctoral researcher of Rios Lab, and I'll be chairing today's panel. And then I'd like to introduce our panelists. So starting from our online guests, the first one is the Mr. Rob Mangs. Rob is the general manager of Chips Alliance. He is a 40-year industry veteran, former engineer vice president of Oracle, and Sun Microsystems distinguished engineer. He has over 35 years of experience in the software engineering and with 25 years of experience as an EDA software architect focusing on the microprocessor design and advanced process node technologies. And second, we have Johan Euphrosine is a developer relations engineer in Google Japan, focusing on improving the developer experience of open silicon toolchains. And we have been collaborating on the open MPW projects and also the Vizier hardware optimization on the cloud. And we have our offline guest, Dr. Fengwei. He's an associate professor of South Tech University, and he was also an associate professor at Hiroshima University in Japan. And he also has extensive experiences in advanced ASIC design for DSP, image recognition, machine learning, and so on. So without further delay, let's get started. So the first questions and the topic in today's panel is, what do you guys think is the major challenge of the open source hardware as compared to the traditional open source software? And what do you think we should do to protect the intellectual property in the open source ecosystem? Can we start from Rob?
Sure, yeah. So I think a major challenge in the open source hardware arena compared to software is that a lot boils down to building trust and validating the underlying IP that you start with perhaps as a building block. Similar like in software, when you pick up a component, right, and you use that to construct additional IP on top of that. What you want to know is that the IP that you are picking up from an open source repository, say like in Chips Alliance, I'll use that as an example, that you know that that IP has been validated. And that means then that associated with that, there is records of that validation having occurred. It could be the actual verification suites, it could be proven silicon as an example, et cetera. But it will give you some degree of confidence that that actually works. In terms of protecting IP that is used or built upon that, that's a similar type of thing in software where you may put your own secret sauce or your own design on top of existing hardware IP or RTL that you pick up and use. So in fact, today I was in a conversation with some major players about a particular piece of IP that they're considering open sourcing that you could then use to build higher level IP on top of. That itself could be protected by the company and not shared back to the open source community as an example. But the key underlying thing is that the foundation that you build upon relative to IP description, hardware IP description, is that you know that it is validated, that it is correct.
Thanks, Rob. Johan, could you please share your...
Yeah, I agree with Rob, packaging is a very important aspect of open source software, and we've seen ecosystem on the software side, around Linux distribution, for example, being very efficient at creating some QA on top of existing open source software block and giving assurance to the people who get those packages that those packages are working well together. And if we're going to start an ecosystem for for hardware, we're going to have to create something like that, and reuse some of the recipe that the software world has found around packaging and try to adapt them for hardware, so that like Rob said, when people get a piece of open source IP, they have confidence that they can reuse and combine it with other works. The other aspect that I think, which is a challenge between open source silicon and its proprietary equivalent, is that often inside the proprietary world, there will be an open there will be proprietary tools, proprietary PDK, proprietary IP that are tightly tied together and often tied to a given foundry or process. And that means that if we want to start anything on the open source side, we'd have to have at least an open source example of all those parts. So it means that we need an open source PDK, we need open source tool, we need open source IP, so that people can have an end-to-end flow that's open source and that can work for them. And so I think the primary advantage that we will have compared to proprietary alternative is that ideally, those combination of open source PDK tools and IP are done in a way that encourage choice and portability, rather than locking the developer and the designer in a given foundry vertical. And so, yeah, that's for me that the primary kind of difference between the open source and the proprietary silicon world. And for the how do we protect the actual intellectual properties of open source silicon work? I think that if possible, we should make sure that we build as much as we can on the existing license that work for software, and make sure that we don't even esoteric license that create incompatibility between work. And so I think that, for example, the work that I think presented on IPH2 just before looks very promising.
Okay, thanks.
Okay, thank you. I think before we talk about the challenge, and firstly, we should be aware of the design difficulty between the software and the hardware. Because I'm a designer, I'm a hardware designer, engineer. So at least, for example, and when we design just verifying algorithm in software, the design cost or effort is very short. Just maybe 1 week we can finish that the algorithm verification. But when we transport to the hardware design, it takes maybe more than 1 month or 2 months. And this is just RTL design. Afterwards, maybe we have to do a lot of verification and maybe the testing, and maybe we have to use many cases for the verification. So the barrier of the hardware design is much higher than the software design. So we have to be aware of this, and then also maybe how to protect the IP and the hardware design, and it's more important. And because, for example, a designer or maybe just share their design, maybe their design has taken about maybe half a year, and then so if there's no one to see a thank yous or something, and then maybe this design will be a little disappointed, I think. So maybe the how to protect, maybe at least maybe we have to build another system to just maybe to give them a good reputation, or maybe if a student or someone engineer, then give them a reputation, and then this is good maybe for their career, and then maybe this is a way for protect the IP, and including maybe the challenge would be the hardware design is a little, the barrier of the hardware design is high, so we have to give them some maybe some retains, and then for protect them, and then maybe give them retain maybe for the career part. Thank you.
Thank you, Dr. An. And the second topic is how can we build a sustainable and a healthy open source hardware community in terms of how do we set the open source policy, and also how can we attract the like the developers and the users to help grow and enlarge the community besides the exception of the IP cost. So similarly, we'll probably still start with Rob.
Sure. I think that's a very good question, and in some regards, the open source hardware community is in its infancy, if you will. Right? There's a lot of excitement and a lot of buzz about it. Certainly, as we've seen some of the different venues and data, like Rick had shared earlier. And I was at the Design Automation Conference here in a couple of weeks in San Francisco. They have a whole open source pavilion. But I think to really start building this, it's going to take contributions from not just minor players or hobbyists or universities, but also investment by major companies, similar to as what happened with the advent of Linux, is that by having major companies starting to participate in this arena, that will start to build credibility. And it also will build quality as well, because larger companies will be able to put more resources into verifying IP and also publicizing that things actually can be built. Again, not that smaller players cannot do this, but I think having larger companies participating in this will really help to start accelerate the belief in this. I recall back earlier in my career that Linux was something just a hobbyist that some of the colleagues I worked with years back at IBM, they would go play with and tinker on the side, but it wasn't anything really serious. It wasn't until different players started getting involved, larger players or companies such as Red Hat saw it as a business opportunity, that we'll see the same type of thing for hardware IP also in this regard. And what was the other part of your question? I didn't quite catch that. I'm sorry, could you repeat the question again? I missed the last part.
Yes, is the how can we attract more like developers and users to the community besides the like exemptions of the IP cost?
Okay, I think a lot of work is going into this in terms of trying to attract people to the hardware community, and I'm sure as many on this call know as well. But when I chat with some of the different university professors around the world, it is a real challenge to get people interested in hardware development. I think a lot of effort is being put into helping automate the hardware development cycle compared to what existed in the past, and making it more software development like. And that is, as a result, taking away some of the complexity or some of the underlying physical difficulties of doing chip design. That's making it easier and more attractable to a wider audience. So one example, which I found interesting, I was chatting with a person with the state of New York here in the United States that will be funding a certificate program to enable people to learn how to do chip design. It's not a college degree. It's more like what would be called classically a technician's degree, right? Or an associate degree, maybe it's a better term. But effectively, it's a short program to allow you to learn chip design and to be able to do it. The other aspect as well, of course, is really overcoming the fear of failure, right? That's something that, of my timeline, that's certainly something that was instilled in you, is a fear of failure relative to silicon development. And that's something else that has to be changed. And of course, with some of the process technologies that are not available for widespread usage, that has made that much more approachable as well. Thank you.
Thanks, Rob. Johan, could you please share your comments? Thanks.
Yeah, so I think that in order to bootstrap or grow a community, like you need two things. You need like people. So we want like a diverse group of contributors, like coming from software engineer, like hardware engineering, like startups, like industry or academics. And we need also a project seed, like some open source bits that's already there that people can contribute to and build on top of. So I think like once we have those two things, like we can grow, we can start like growing the ecosystem. I think like for the open silicon ecosystem in particular, it means that we need to bootstrap, like we said before, and I think Tim also touched on that in his presentation. We need to bootstrap the whole stack, coming from PDK to tools to IP, so that like the community can feel empowered to consume that and build on top of it. And the other thing that you mentioned around like growing the community, I think like it's very important that we get a smooth getting started curve on all the things, so that like people coming from different backgrounds, for example, from a software engineering background, can easily like reuse this tool and find themselves familiar inside this ecosystem, and can also, more interestingly, bridge their existing workflow or bridge their existing tooling with the open silicon tool chains. But it's also important that we take care of the transition within the ecosystem once they are already in. So it means like, how do I become a contributor when I'm just a user of the tool? Like you need to kind of lower the barrier for people to contribute patch to this open source tool, to get familiar with the contribution workflow, and to get more familiar with browsing the code base. And like the other aspect, which is especially relevant inside hardware, is that how do I go from like prototyping to production? So I could start with an open MPW shuttle, but once I want more volume, like do I have a way to just reuse my design and submit it to another shuttle that can provide me more volume for money? So we need to have like all we have to have like those bridge that bring existing people from other community, but we also need, once they are in, to find kind of build a smooth ladder for them to go through the step of like starting with a prototype and going successfully with something that they go at volume in production.
Exactly, and before talking about the now the successful open source community, I think maybe there is a not so successful case. Some may know open cause, right? And exactly open cause has been running maybe over 20 years, maybe over 20, about 23 years. So until now, just the last night, I searched for open cores, and there are about 1,200 projects has released, and the last updated is was maybe in May of 2021. So maybe, oh yeah, more than 1 year ago. Yeah. So what has happened over open cores, and it is just maybe open source hardware and the community. And so on the other hand, maybe we can talk about now RISC-V. It is a good maybe a good case, good example for the open source community. And now it has been maybe maybe 2000 2,500, I remember, and the community is about the RISC-V open source. So, and also in China, there are T-Head and Sci-Fi, and so some company, and now to release some commercial and RISC-V and hard cores, and maybe not soft cores. So, and then, and also team has introduced about the open MPW. Now they are only 3 years. There are 250 projects has been successfully shipped out without any DRC errors. So that's very I mean attractive news for the open MPW. So what had happened for the RISC-V and open MPW? Why? So maybe I think about and how to build a community before that. Maybe it's the leading force. Now, and also today we are talking about the open source hardware, and because the invitation from Royce, right? So the leading force and has played a very good and also important role for this community. And also now the open MPW is held by and also by Google. So the leading force is very important. So they can associate associate the university and the research institute and also some leading enterprises. So this is very very important, And another question is about except for the cost and so how to the that that would be the I have said about maybe we can give the designer some reputation, and also the social media now is very popular. For example, the Twitter and the Facebook. So we can give another, maybe build another community, and also like the social media, and to give them um, um, some comment about the reputation, and then that would be help them to find a good job or something. Maybe this would be more important for the designer, I think, because they are self-motivated. So let's just with a fund to open their maybe design. So maybe this design and for example, and recently we also searching for a lot of maybe designs about the PNG decoder encoder. Maybe someone know about the JPEG and the PNG decoder encoder, but there's almost no open source for that. So we have designed the encoder and the decoder. Also, we talk with I talked with my students. It is possible that we open that. So this is the just self-motivated and just with the fun. So maybe the reputation may be more important than the cost, I think.
Thank you. And the third topic is, what do you think of the impacts posed by the open source evolution upon the commercial IPs? And how do we encourage the commercial competition while still advocating the open source community? Rob.
So I think, yeah. So I think there is definitely opportunity for both parties to play side by side. And specifically, what I'm considering is that I think there's opportunity for commercial suppliers to validate and possibly build both either soft or hard IP that is used in the open source community. So there certainly could be things that are proprietary that you have to license through a IP provider. That could be proprietary rather because of what's encapsulated in the IP that you are licensing in terms of algorithmic technology. It could also be because of process technology. But it's also possible, though, that the open source technology could be validated and supplied as a macro from a commercial supplier. And the reason I think that this is viable in part is because companies who I have talked to, they're very interested in open source. They'd like to be able to see what's actually inside of the macros. But on the other hand, they want to know that they have a company to call as an example to get support on particular issues, or to make sure that what they are actually using is good, right? And they want a company to be able to stand behind that. At the same time, though, there's definitely opportunity for true open source developers, if you will, and open source tool developers as well, to work on the same type of IP and provide a different type of business model for that to be deployed and used by the community. So I think it's definitely a hybrid type world that could exist. Now, for IP macros that are built on the latest advanced silicon technology nodes, that's a different conversation, right? Because then that gets into understanding what the silicon developer is doing in terms of the PDK as an example, and also the underlying device structures that would be available. And that's a longer conversation, I think, relative to having a mixed environment between open source and closed sourced IP. Thank you.
Thanks, Rob.
Yeah, so I wanted to comment first that I think that the distinction in the question between open source and commercial, I think, is a false dichotomy. Like software has shown that you can have like commercial exploitation of open source work like multiple time, and so I think it's more about like and it's even more true in hardware where you can manufacture actual artifact out of an open source world and like sell them. And so, yeah, I think like the real question is like, how do we make sure that proprietary tools and proprietary IPs can collaborate and be combined with fully open source work? And I think like a primary thing that will need to happen for that, and we already see that happening inside the FPGA world, is to come up with a set of standard format or interoperability format or intermediate format that or interexchange format that could be used by multiple tools to exchange like file together. And so I think, yeah, it's like there is a FPGA interexchange format that started to be adopted by a strong industry, even proprietary player. I think that's very encouraging also for the ASICS world to try to find those formats, document them, and try to get like open source and proprietary tools alike to adapt to them and enable like design to flow between tools.
Thanks, Yuan.
Okay, maybe the open source hardware. Firstly, open source hardware is free access, and also with no payment. And then there's another advantage would be the open source hardware is apparent to the designer, to users also, maybe the users. And if the users have enough maybe technical expertise, and they can change the design, and without any maybe the license problem. But and also rather than the commercial IP and just profiting from the maybe selling the copies of the IP, and so maybe the open source designer also can get some maybe feedback from the customization. And so this also would be the disadvantage advantage of the open source. But there's someone still want to use the commercial IP, because in the silicon, I mean in the hardware design, chip design, silicon proven is more important. So silicon proven is not mean, it doesn't mean the MPW. Maybe someone will ask, do you have any massive production proof? So this would be more important, because the commercial IP can support the well-defined documents, and so also other technical supports. So I don't think there's there a lot of effects because of the open source to the commercial IP. So they may have also a good balance. Finally, I think.
Thank you. And now we have our last topic is regarding the cloud computing and the open hardware design. So what do you guys think of the cloud in terms of accelerating the open silicon research, and how can we leverage it to foster the high quality open source IPs and the open source community?
So I think cloud computing is a tremendous accelerator in general for chip design. So if you look at my background, one of the roles that I had was with Qualcomm, which makes the chips used in your cell phone. A 5G modem is of course the classic example. But in terms of managing their compute infrastructure, they regularly worked very hard or diligently to balance workloads across multiple geographic locations, because they were constrained, as all companies are prior to the cloud, to the actual available compute resources. And to expand that was a cost or capital equipment expense type of challenge. There's also time of building. So I think having effectively infinite compute capability, such as what Google Cloud offers as an example, but of course you can get that from Microsoft, IBM, Oracle, to name a few, it offers a real opportunity to accelerate the design and verification of hardware design specifically. Now, also the challenge of that, aside from the cost of having the being able to expand dynamically to needs, of course, is ensuring that the EDA algorithms scale with that as well. The other thing is, which is what cloud or containers allow for, is a consistency of compute environment for the chip designer. That simplifies things a lot as well. So what may not be known to the audience, or maybe it is, but companies spend quite a bit of time and resource in terms of developing a design environment that ensures consistency for all designers. And there's also, as well, correspondingly, a fairly large IT staff that maintains all as well. So being able to effectively outsource the IT problem to a cloud provider, having containers that can be created, say maybe that's provided by an EDA company, maybe it's provided by some type of open source company that could develop containers using open source EDA tools that provide a consistent environment, that accelerates all of that. I know eFabless has done a lot of this work, and that certainly has helped a lot take away much of the complexity that's needed or happens in this. So in general, or in summary, I think cloud computing is a tremendous enabler to time to market and accelerating the overall open source movement. Thank you.
Thanks, Rob.
Yeah, so yeah, I agree with everything that Rob said, but I wanted to add on top of that that there is like a good demultiplication that happen when you combine like open source software with the cloud, and especially more inside the open silicon ecosystem, because once you use like open PDKs, open tools, and open IP, you're not restricted anymore by like license system or NDA that you might have with the foundry to prevent even from bringing you from running those tools or using those PDK on more than one computer. And so when you don't have this restriction anymore, you can do things like Rob was saying, like spawning infinite compute resources to finally be able to explore like all the corner case of your design. So you could run like 1,000 experiment to find like the best ratio between like area and density for your RISC-V core, for example, and really fit and find the best parameter for your application that you currently want to do. So for example, if your application currently is a low power profile application processor, so therefore like you want to try to reduce the power consumption, but maybe you have like another project where you want to extract the more performance and you don't care so much about power, and then you can like spend like another 10,000 experiment to explore like the design inside a different direction. And like because and if you combine that with the power of like generative design and open IPs, it means that other people can take your work and do like different exploration into like what they care for their specific application. So I really think that there is like because everybody kind of want to have different constraints for like the actual production work that they want to do. There is like a good demultiplicator here that can happen where you actually spend the time and the resources to find the best parameter for your design. And the other thing that I wanted to add on top of that is that we should take lesson also from what has been done inside the software world, inside the data science world, and maybe inside like the machine learning world, where they completely adopted the tool for running like all of their workload. And like one thing that I think is especially interesting is what is happening around Jupyter notebooks and those like interface that combine like documentation, actual code that you run, the output of the output of that code, and like the actual command that you run to orchestrate your workflow and the result. And so that at the end of when you get a notebook from someone else, you get a fully reproducible flow of like a given computation that was run. And that's very good for ML when they want to distribute like a reproducible like version of their paper to show their research. But I think it could also be true for silicon design, where we have like a lot of parameter to tweaks, we have a lot of different tool to launch, and we had a lot of graphs and metrics that we can plot at the end to kind of explore like the design trade-off. And so I think like, yeah, we should try to reuse as much as we can of like those existing tools that are there to perform those computation in those tools, and like try to leverage the fact that having like an infinite compute, potentially infinite compute capability could allow us to do a much more lot experiment that we were doing before.
Thanks, Johan.
Okay, I also agree with that the cloud may accelerate the open source, and exactly one of the main feature of the open source hardware would be, I think, the challenging work, so it is very complex or complicated project. And then what that means, it may take or require many power resource, and so the power resource means the computing resource. For example, and exactly, we have just completed one design and recently, and our design is not so complicated like what I want to see. It's just maybe 28 nanometer is about 3 millisquare, so it's a little small. I think it's not so large, but during the PR, the place and route procedure, each time the route will take about 4 hours. So you may say, your server is so bad, that's just super, but it's not so bad, and it has it has 8 CPUs. Each one has 48 cores, so it's very good server, I think, but it still take a long time for just we think just a very simple and operation. So if we can use in the future, if the open source, maybe the first and there's a complex project, so it will requires a lot of computing resource. So at that time, the cloud certainly can accelerate the open source and the hardware design. Thank you.
Thank you. Thank you very much for the inspiring discussions and all the comments we have from our audience. Now we are try accepting the questions. Do we have any questions for our speakers?
The first one in our open port chip. Advanced process node. For example, 22 nanometer, our most advanced process node. So how do you think about these 2 problems, and how to face these problems?
Could someone possibly summarize the question? It didn't come through all the way here for me.
Okay.
You are breaking up.
Okay. There are not many IP cores in our open process. So how to face these problems?
Yeah, I don't understand. Yeah, I do hear you. I don't understand the question. Maybe Johan can take it for me first. I don't know, or try repeating again.
For example, in the open MPW process, we didn't find many digital or analog IP in process PDK, our process library. But when we design, we need more IP core to accelerate the design.
Yeah, I think I got like part of the question, the fact that the ecosystem is still nascenting, and that we there is not a lot of IP for people to reuse yet. So there is like definitely a chicken and egg problem there, where like if you don't have enough IP, like it's more difficult to attract contributor to build like interesting derivative work on top of those open IP. I think we have a good seed with the existing PDK, and like with the Open MPW program. That's what we are trying to do. We are trying to come up with sponsoring like realization of silicon, so that like people are more incentivized to create those open IP blocks. So like we have like we see like a steady like 20% growth across like every single PDK. So it means that we've got like 20% more design every new for every single like open MPW shuttle that we run. And now we have like more than 350 design. What's interesting is that as part of those design, there are also design that are resubmitted, meaning that it's not only about coming up with just new IP block or new project. It's also about taking existing project and making them better. And so I think that's also like, you have like two axes there that you need to consistently explore. Having a lot of IP is good, but like the open core project have shown, like you have a lot of IP there, but if they don't get updated and maintained, that's not good. And so you also need to get like those NP maintained and resubmit it to the shuttle and revalidate it over silicon. And ideally, when we get more PDK and where we get more foundry to organize your shuttle, you'll be able to port and validate like those technology, those like project across like many different technology. And the other aspect that I think is really important is to empower research. So I think a lot of those interesting IP actually come from the academic and research world. And if you look, I was going to the VLSI symposium 2 weeks ago, and I don't know much about hardware, but when I was like, because I mostly come from a software engineering background, but when I was looking at the figure of merit that got projected on each of those presentations that were presenting an innovative design, like there was a column there about like the PDK and to compare like their work to other work. And like every single column was using a different PDK, which means that basically the number that you get there are really hard to compare between each other, because like they don't use the same technology, so the trade-offs are different. And so I think that if we come up with a baseline, like an open PDK that everybody can use to realize that work and make their work reproducible, that's where we would get more quality IP, because now suddenly people will be able to reproduce each other's work and to compare it with each other using the same baseline. So meaning that you could choose like to reuse work that's coming from this research because like maybe the power profile is more interesting for you. And so I think that, we've done quite a bit of work on the Google side to try to empower like those researchers and try to give them a grant so that they can do the research and make it reproducible. And I think that's something that we want to continue to do, because I think that's very, very important to seed the ecosystem with work that comes from the state of the art of the research that's being currently done on semiconductor.
I would just add to that, something that I understand the question correctly, but I think this will help build an IP portfolio by using a common open source PDK. And also that if the community uses open source tools as part of this, that will help improve that as well. It will also give people experience or information relative to how these tools work. They will not be a black box, so to speak, a secret, which is often the case from commercial tools that you might license.
Thanks, Johan. Thanks, Rob. Due to the time schedule we have, we probably gonna delay the questions to the like offline discussions. And again, special thanks to our speakers and all the panelists for your valuable time and inspiring discussions we have. So next session.
Yeah, thank you. So next we're gonna have a short period for
Bye-bye.
tea breaks. Thank you.
Bye-bye.
Bye.
Thanks, Rob. Thanks, Johan. And thanks, Dr. Ann.
Yeah.